Hey everyone, welcome back to Probability Theory. This will be lecture 12 of the course. And in this section, we're going to just briefly discuss the idea of a discrete random variable. So let's go ahead and jump into it. And we'll call this section 2.1, Discrete Random Variables. And so in the previous lecture, we defined a random variable. We said a random variable is a real valued function defined over a sample space. So a random variable is a real valued function defined over a sample space. Okay, and so we had several examples from the previous section. An example here, just to kind of build up a little steam, would be to say, like let y be the random variable that captures the sum from rolling a pair of die. Okay, so I roll a pair of dice, I record the numbers, and I add them together, and I load that into this random variable. Okay. So you can imagine you've got a sample space, and in that sample space you've got all of the outcomes of these rolls. So maybe you got 2s, and you got 3s, and 5s, and 4s, and 8s, and so on. Okay, and so these are the random variables. This is the sample space S that the function y, the real valued function, is defined over. Okay, so there's a probabilistic quality to this variable y, and that's why we call it a random variable. Now what we want to talk about here is, what do we mean by discrete random variable? And so what does that mean? So a random variable is said to be discrete if it can assume only a finite or countably infinite number of distinct values. So this is all about how many values this thing can be assigned, right? So we say a random variable is said to be discrete if it can assume only a finite, or countably infinite number of distinct values. Okay, so what the heck? So for some of you, this will be like very straightforward. If you've been through calculus, for example, or certainly if you've seen real analysis. But so obviously a collection of a finite number of outcomes we call discrete. Okay, so that part's not tricky. So all of the examples we've seen thus far have been discrete random variables. The example above here, rolling a pair of dice, has 10 potential outcomes, something like that, in the sample space. So obviously it's finite, and therefore it's discrete. This other idea of countably infinite is a little more is a little less obvious, right? So what do we mean by that? What we really mean by this, and there are different ways to kind of approach this, but really the way to say this is, can you list all of the values that the random variable can assume? Can you list, and we'll talk about what listing means, can you list all of the possible values that the random variable can assume? Right? So obviously if it's a finite set, you can do that, right? But this does allow for countably infinite sample spaces as well, or countably infinite number of distinct outcomes for your random variable. And so really what we're saying is, can you make a list, given an infinite amount of time, would it be possible to make a list of all of the possible values that your random variable would take? So for example, the integers right? Well, let's take the integers, right? We know the integers are 0, plus or minus 1, plus or minus 2, and so on, right? It goes on forever, infinite set, right? However, it is possible to list these numbers, and not least of all because you can present it in roster form like this. So it is possible to list all of the integers. Okay, and so therefore we would call any random variable that had the entirety of the integers as its potential outcomes, we would call that a discrete random variable. So if y is any value that's in Z, we'd say y is a discrete random variable. Okay, and the same is actually true, obviously, of the natural numbers, the counting numbers. This is really, everything's kind of, this idea of countably infinite is based on really the idea of the counting numbers. The integers are another example. Even the rational numbers, the set of all fractions, those are also a discrete set. So even though there's infinitely many of them and I can't explicitly write them all out, I can come up with a rule for how to write them out, and i.e. I can list them. So that is what we mean by a discrete random variable. So anything that can be kind of listed. Now, I want to all of the random variable examples we've seen so far have been discrete random variables. So instead of giving you more examples of that, what I want to do is give you an example of something that isn't a discrete random variable. So an example of if a random variable isn't discrete, it's called continuous. Or an example of a continuous, so non-discrete random variable is the following. So here's a nice example. So let's let x be the amount of time in minutes it takes for a bus to get to your stop. The amount of time it takes for a bus to reach your stop. Okay. All right, so we're talking about time here. This is a measurement of time. Now, if you think about this, like depending on how sophisticated your time mechanism is, the values of x are going to be things like 5.3 minutes, 7.02 minutes, 8.9876 minutes, right? And so clearly in reality you'd probably come up with a hard cutoff here, but theoretically speaking, these times could take any value between 0 and some theoretic threshold. So theoretically x is just inside the interval 0 up to, we'll say 20 minutes. Maybe you've got some reasonable upper limit. Right, now within this interval, there are infinitely many different times that you could potentially measure for the time it takes for the bus to reach your stop. Okay, and so for that reason, x is a continuous random variable. Now you could make it a discrete random variable by identifying some level of precision, right? Maybe you say you're going to round everything to 1 decimal place, so 5.1 minutes, 5.2 minutes, 5.3 minutes, or you're going to list it as whole minutes, whole seconds, and then some agreed upon fraction of a second, right? So in some ways, this is a little bit of a pedantic and strange example, but what I'm trying to illustrate is it's this concept of time is continuous, right? It isn't discrete. It doesn't come in with gaps in between, right? So for example, it could take 8.00376542101 and so on minutes, right? Theoretically. Of course, it would be very difficult to measure that, of course, but the idea is that time is continuous. It's not a discrete thing. It's certainly different from the examples we saw earlier, such as rolling a pair of dice, right, where you have basically 10 outcomes and they're very straightforward. It's even different from the case of like the integers, 0, 1, 2, 3. I know what this does forever, but over here, these kinds of numbers that have these infinite decimal expansions, they're not really what we would call countable. So these types of numbers are not countable. And so that is a topic for a different class. Really, if you want to understand that, you have to go and take a class called analysis. Beautiful class, highly recommended. But all we need to know is that in this case, the random variable time is not a discrete value. It exists on a continuum inside of an interval like this. The real numbers, specifically between 0 and 20 minutes, are a continuum. They're not discrete. Okay, very good. So that's all we wanted to talk about here in this section. Now in the next section, we'll get into what is called the probability distribution. And so specifically, we'll begin with probability distributions for discrete random variables. And then later, after we've covered all of that material, we'll get into probability distributions for continuous random variables. We want to kind of partition them off because the one is a little bit more straightforward and easier to understand than the other, and the other involves calculus and integration and everything. And so we kind of want to start with something a little bit more simplistic and then work our way up to something a little more complex. All right. Until then, take care.